Hello viewers, today in this part of the presentation we will continue to discuss sequential logic design, and the outline for today's discussion is as follows. We will start the discussion with the note of modulus of a counter, then we will discuss 3-bit synchronous up counter, then we will go to 3-bit synchronous up down counter, then we will discuss ring counter and a typical type of ring counter, that is Johnson ring counter, and finally we will discuss pattern detector. Modulus of a counter. So, modulus or mod of a counter is given by 2 to the power of n, where n is the number of bits. Now, if we try to understand it by considering an example, then we can write the modulus of a 2-bit up down counter as 4. So, in the similar way we can find out the modulus of a 3-bit or 4-bit counter is equal to 8 and 16 respectively, and hence they are called as mod 4, mod 6 and mod 16 counter respectively. Now, let us try to construct a mod 6 counter from a mod 8 counter. So, for a mod 6 counter, the number of states will be equal to 6. So, the corresponding maximum number that it can count is equal to 5. Similarly, the number of states that can be counted by mod 8 counter is equal to 8, and the corresponding maximum number for the mod 8 counter would be equal to 7. Now, since we have 5 as the maximum number for mod 6, so we have to stop somewhere after 101, because 101 represents the binary representation of the decimal number 5, and so we have to construct a circuit such that it will fulfill the output condition. So, after the desired binary number, we have to reset the counter to 0, 0 and 0. For that, we connect a NAND gate to the clear input, and the inputs are QC, QB and QA. So, here we have shown the 8 states involved in mod 8 counter, which starts from 0, 0, 0 and ends at 1, 1, 1 as the output. And here we have shown a dotted line, and above the dotted line the binary representation that we have is 101, and that is the output that we are looking for from a mod 6 counter. So, as I said that we have to have the output as QC, QB and QA. So, once it reaches 101, the next state is 110, which we have to reset as 000, because we want the counter to count till 101, which is the binary converted number of decimal number 5. So, one can create in this way a small mod counter from a larger mod counter. Here for our example, we created a mod 6 counter from a mod 8 counter, and here in this slide we have shown the logic circuit for the mod counter that we created from a mod 8 counter. Here we have used 3 JK flip flop, and the output and the clock and the clear inputs are combined in such a way that in some way they are connected to a NAND gate. Now, let us discuss about 3-bit synchronous up counter. So, to construct a 3-bit synchronous up counter, we have to follow the steps given or discussed in this particular slide onwards. So, first we need to find out the number of flip flops and the type of flip flop that is to be used to construct a 3-bit synchronous up counter. So, let us consider a T type flip flop and the corresponding truth table for T type flip flop is shown in this slide. So, here for the truth table we have 3 columns, that is clock, then input T and the next state q n plus 1. So, when the clock signal is 0, irrespective of whatever the input signal is, the next state will be the non-changed state, that is the present state. But when the clock becomes 1 and the input becomes 0, in that condition also the next state is equal to the present state. It is only when the clock is 1 and input is 1, it will start toggling, that means the next state will be complementary to the present state. Here we also have shown the symbol for the T flip flop. The excitation table for T flip flop is also shown in this slide, where we have the present state and the next state as the input condition and the input as the output condition. For example, when the present state and next state are 0 0, the input must be 0. Similarly, when present state and next state are 0 1, the input is 1. Present state and next state are 1 0, the input is 1, and present state and next state are 1 1, the input is 0. So, once we have considered the number of flip flops and the type of flip flop we want to use, we have to find out the state diagram by considering the output that we are looking for, because here we are considering 3-bit output. So, the number of state has to be 8 and the maximum count that it can do is equal to 7. So, here the state diagram is also shown in this slide, and as you can see, the state starts from 0 0 0 and it will go till it reaches 1 1 1, and the arrows show the path that the states follow in the subsequent state signals. So, now from the state diagram we can easily obtain the excitation table, which is shown here. So, here we have broadly 3 columns, that is present state, next state and the input. So, the present state, because we have to have a 3-bit counter, so we need to have 3 flip flops, and for the 3 flip flops the output and the inputs must be coming from the 3 flip flops. So, here for present state the outputs are QC, QB and QA. Similarly, for the next state the outputs are QC dagger, QB dagger and QA dagger, and the inputs are TC, TB and TA. So, here you can see the excitation table shown in this slide depicts the present state, the next state and the input condition that can be obtained for the 3-bit synchronous up counter. Now, once we get the information from the excitation table, now we can solve the K map for each of the inputs from the flip flop. So, for TC we can use the following K map, where the vertical section is QC bar QB bar, QC bar QB, QC QB and QC QB bar, and the horizontal rows are QA bar QA. And if we solve this K map, then we will obtain the output y is equal to QB dot QA, which is the complementary inputs for TC. Similarly, for TB we can write the K map in the following way, where the horizontal column is represented by QC bar QB bar, QC bar QB, QC QB and QC QB bar, and the horizontal rows are QA bar QB. And if we solve this K map, we will get y is equal to QA, and that is equal to TB. Similarly, for TA we can get the K map that is shown in this slide, and if we solve the K map, then we will get y is equal to QA bar dot QA, and that is equal to 1, and that is equal to the input of the A flip flop, that is TA. So, after solving the K map, now we can construct the 3-bit synchronous up counter, and the logic circuit looks the way it is shown in this slide, where we have used 3 flip flops, and these are T flip flop, and the clock is connected to all the 3 clock signals of the 3 flip flops, and there is a combinational circuit involved where we have used a NAND gate. So, in this way we can construct a 3-bit synchronous up counter. Now, let us discuss about 3-bit up down synchronous counter. So, if we can construct a 3-bit up counter, 3-bit synchronous up counter, then it is very easy to construct a 3-bit down synchronous counter. So, we can follow the same steps to find out the circuit for this counter, which is a more general counter which can do both up and down counting. So, for this, in addition to the input, there is an input mode control M, which we have already discussed in one of our previous presentation. So, here we have shown the 3-bit up down synchronous counters logic circuit, which has the extra input mode control M in it. Otherwise, most part of the circuit is same as in terms of construction process as the way we obtained the 3-bit up synchronous counter. Next, we will discuss about ring counters, and ring counters are useful in shift registers, and these are also called as presetted 1 counter. The circuit for ring counter is shown in this particular slide, where we have used 4 D flip flops, and there is a overriding condition which is represented by ORI, which is connected to the preset of the first D flip flop. So, as I said, here there are 4 flip flops, but the number of states is 4. So, the flip flops are of interest is D flip flop, and the output of last flip flop is fed as input of first flip flop. For overriding condition, when preset is equal to 0, we have to have q is equal to 1, and when clear is equal to 0, we have to have q is equal to 0. Now, since it starts from 1 and comes back to 1 and forms a ring, this type of counter is called as ring counter. So, here in this slide, as you can see, we have shown the clock diagram which can tell us why this type of counter is called as ring counter. So, here we have 6 columns. One is for the overriding condition, the next one is for clock signal, and the next 4 columns are for the output, that is QA, QB, QC and QD. If you follow the arrows shown in the clock diagram, then you will see the arrows are moving diagonally, and once it reaches one of the columns or the last column of the output signal, it again goes back to the column of the first output signal, and in this way it goes on in a ring. And as you can see, the clock signals also show the same kind of feature that you can see in a circle or when things move in a ring. So, that is why this is called as a ring counter. Now, let us discuss about Johnson ring counter. This is also called as twist or switch tail ring counter. Here the number of states is equal to 2 times the number of flip flops that will be used, and the overriding input is connected to the clear input of flip flop. The complementary output of last flip flop is the input of first flip flop. So, these conditions need to be satisfied for the Johnson ring counter, and here in this slide we have shown the logic circuits for Johnson ring counter, where we have shown 4 D flip flops and the clock signal is connected simultaneously to the clock inputs of all the 4 D flip flops, and the overriding condition is connected to the clear input of all the 4 flip flops simultaneously, and on top of that the complementary output of the final flip flop or the last flip flop is connected to the input of first flip flop. Here in this slide we also have shown the timing diagram for the Johnson ring counter. So, Johnson ring counter is better than the normal ring counter, and why is it so? Because the number of states here is more than the ring counter, and here we did not need to initialize the output of first flip flop to 1, because we start with 0 0 0 0 condition. Now, let us discuss about one of the important thing that is needed in digital electronics, that is pattern detector. So, what happens in pattern detectors? Here the stream of bit that is coming to the sequence detector or pattern detector as input, and at that time if the clock is high or the clock signal is high, then whatever pattern we want to detect from the input signal, it can be detected. Now, when the pattern is detected, the output will go high and then immediately it will become low. To understand this in a better way, let us consider the following example. Let the input bit stream is represented by x and that is equal to 0 1 1 0 0 1 0 1 0 0, and we are interested to find out the pattern 0 1 0 in this bit stream. Now, it can be done in two ways. The first way is by considering the overlapping of bits while detecting the pattern of 0 1 0, or by considering non overlapping of bits. Let us try to understand one of the cases, and that is the by considering overlapping of bits. So, here as you can see, we have shown the bit stream with the overlapping bits in dotted lines, and we have made boxes of dotted line to show the overlapping condition. Now, here when the first bit comes, the output becomes 0, because it starts with the input bit of 0. Now, for the second and third bit also it will show 0, because it does not match with the pattern that we are interested with. For the fourth bit also it will show 0. Similarly, for fifth and sixth bit the output will show 0, but as the seventh bit comes, it detects the pattern 0 1 0, and immediately the output will become 1. This is because we are considering overlapping of previous two bits before 0 to form the pattern 0 1 0, because till we get 0 1 it will keep showing 0 at the output, but as soon as it shows 0 1 0, even though it is overlapping, the bits are overlapped, it shows 1 at the output. Similarly, 8 bit will give 0, but as soon as 9th bit comes, it will detect the pattern again and the output will be 1 again. So, there are 3 steps involved to check the sequential circuit. Now, what are those states? Now, let us consider one of the standard state machine, that is the Mealy state machine, and let us obtain the state diagram to represent the circuit for the detection of this sequence. So, as soon as we switch on the sequence detector, it will go to reset state, that is S0, which is the power up state. If the next bit is 0, then it will go to next state S1. So, S1 is equal to 0. If the first input bit was 1, then it would have stayed in the state S0, as it is not the first bit of the sequence. So, if x is equal to 1, then y is equal to 0 and it stays in state S0. If the first input bit was 1, then it would have stayed, as we discussed, it would have stayed in the state S0, as it is not the first bit of the sequence. Now, if the next bit is 1, when it is in S1, then it will go to the next state S2, that is 0 1. So, when x is equal to 1, y is equal to 0, it goes to state S2. While in S2, if the next input is 0, then it will go to state S1. So, when x is equal to 0, y is equal to 1, the state is S1. But while in S2, if the next input is 1, then it will go to S0, which is the reset condition. So, when x is equal to 1, y is equal to 0, it goes to state S0. And note that the reset condition and state 0 condition are completely different. So, now that we know the flow of the input and output condition across the different states, we can now draw the state diagram, and here in this slide we have drawn the state diagram between S0, S1 and S2, and the arrows shows the flow of one state from other state depending on the input and output condition. So, this is the first step. Now, in the second step we need to assign states, that is S0 is equal to 0 0, S1 is equal to 0 1 and S2 is equal to 1 0. So, for circuit building we have to use flip flop, and as we said you can choose the flip flop that you are most comfortable with, and then once we use the flip flop we can use the reduced condition that we have already discussed in one of the previous presentation and come up with the circuit that can be used as the pattern detector circuit. So, viewers, today what we discussed can be easily summarized by following few important points. So, we started the discussion with modulus of a counter and what is the use of modulus of a counter and how one can make a smaller modulus counter from a larger mod counter. Then we discussed about 3-bit synchronous up counter and 3-bit synchronous up down counter, how we can construct these counters by using the knowledge that we gathered from the previous discussion. Then we discussed about a ring counter and then we talked about a specialized counter, that is Johnson ring counter, and what is the difference between the two, which one is more suitable for constructing a ring counter. And finally, we discussed about pattern detector and their importance and how one can detect pattern in a stream bit for the application that one needs to think of. So, viewers, today the discussion is very important for understanding of digital electronics and the understanding of counter, and I hope you would have liked today's discussion. Thank you very much.